Good morning, gentlemen. Today I will be speaking on the special platform design for deep ocean mission. Though I have been associated with Bixanbit for 14 years and I have had the opportunity to design the naval auxiliaries, today I'm going to take a little bit deviation from the classic marine and naval architecture and then go into a different area which also needs platform design. This is something called a deep ocean mission. As you would have heard in these recent last couple of weeks, the government of India has sanctioned about 4,000 crores of rupees for this deep ocean mission with a very focused target to develop deep sea technologies. And by meaning deep sea technologies, these are not the normal ones. And we will see what these deep sea technologies are there. There is a scope for several kind of innovations, several kind of innovative ideas. So as a classic quote says, need is the mother of invention. And then that is the reason that we have been working towards trying to eliminate the fossil fuels, trying to bring in the renewables. This has led into electric revolution, what we call EV revolution in the passenger cars. And also it takes the revolution into marine in the form of hybrid ships, the form of battery technologies. So all these revolutions and all these requirements lead to a requirement of minerals, very strategic minerals like copper, cobalt, and nickel. And that's what today I'm going to talk about, because eventually somebody thinks at least 10 years or 20 years ahead of time before the actual need comes. Then you are really prepared for it. That's what is happening today. So I just want to take you through what's happening in this scenario. So the outline of my presentation is like this. I will be talking about the polymetallic nodules. They are the potential mineral resource from deep ocean. There are several potential resources from deep ocean, but today it's very difficult to cover all of the mineral resources. But then I will take the polymetallic nodules as an example, then take you through where we are, what are the challenges in the approach, and then what are the platform design considerations and the environmental concern in this. So here we are. So what is, just a second, there's a panel that's coming up in the presentation. Let me try and hide this second. Okay. Deep sea mining. So what is a deep sea mining? The deep sea mining is a classic, what we can say is a process of extracting minerals from the deep. When we say extracting resources from the deep, it could be a resource from any part, like from the hydrothermal vents or from the sea mounts or just plainly digging up the ocean. So here, when we say deep sea mining, what is deep sea? Usually, the deep sea is considered to be greater than 200 meters. We can even say 300 meters because the saturation diving depths are more or less limited to 300 meters. So more than that is called a deep sea. So what we consider, what are the resources that are available in the deep sea? There are several of the resources available. For example, at about greater than 200 meters in the seas of Andaman, you have polymetallic sulfides from hydrothermal vents. Hydrothermal vents are nothing but hot springs underwater. They have very rich mineral deposits at that particular place, 1,000 to 4,000 meters, like copper, gold, zinc, lead, barium, and silver. And then there is, if you go slightly deeper, then if you go slightly deeper to 4,000 to 6,000 meters, then you have these polymetallic nodules in the upside plains. They are in the several places like Central Indian Ocean Basin, as well as in the Pacific Ocean in the Clarion-Clipperton zone. They are very rich minerals like manganese, iron, nickel, copper, cobalt, and molybdenum. These are especially the cobalt and nickel. They are very, very strategic metal. Also copper, very strategic metals, and these are the ones that are driving. If you see what are the drivers, These are the ones that are driving these deep sea mining, especially on the EV revolution. These are the cobalt and nickel, copper, cobalt, and nickel are the minerals that could replace the potential land resources that is available today. So maybe in the future, when we have very, very less of fossil fuels, maybe we need to rely on these deposits for this. So we need to develop technologies for these. That's the idea. Then we also have in the lesser depths, say from 800 to 2,500 meters, we have ferromanganese deposits, predominantly manganese and iron. They are available off the coast of Ratnagiri in India. There's also a huge survey and mining efforts going on for that. But then who regulates the seabed? Because most of these are available not in the exclusive economic zones of countries, but in the public area. So there is an International Seabed Authority, ISA, where the countries are members, and they regulate this mining of these metals. So, like I said before, today I talk about polymetallic nodules. What you see in the picture is the potato-shaped nodules. They are just lying in the seabed around 5,000 meters plus in the ocean. They are available in two areas. One is in Indian Ocean, Central Indian Ocean. Other one is in Pacific Ocean. The Pacific Ocean has much more higher density of these nodules, and Central Indian Ocean lesser density. But then this has very, very strategic minerals, like I said, copper, cobalt, nickel, and manganese. So today I limit myself to the Central Indian Ocean Basin, and where India has got a area reserved for exploration and mining. So this is available in the Central Indian Ocean Basin. The amount of area that is available is 75,000 square kilometers. And the area is about 6,000 kilometers south of Kanyakumari in India. It's in the Central Indian Ocean Basin. The International Seabed Authority has given us a 15-year contract for exploration, developing technologies, and even extraction of metals from that. So, what is the amount of minerals that is available? The total number of nodules, that is about 380 million metric tons of nodules, are available in the area allotted to India. And the amount of strategic metals is about 1 million tons of cobalt, 5 million tons of nickel and copper, and about 100 million tons of manganese. Though manganese is very abundantly available in the land resource, even we have a higher resource in the deep sea. So these are the much needed minerals for the electric vehicle revolution, or even for the hybrid or the battery operated ferries or the solar ferries or the solar operated ships, solar renewable ships. For everything, you need these strategic metals. So what is India doing in this? In the Indian Polymetallic Nodules Program, or this was recognized way back in 1982. 1982 was the time that India discovered these nodules in the Central Indian Ocean Basin. And then they did that for 10 to 15 years. They did the survey, exploration, and stake claims to the International Seabed Authority that we will be a pioneer investor, we will spend money, we will explore this area, we will develop the technology, and then we will be ready to extract the minerals. That's what was a strategy of India in this program. And the institutions, National Institute of Oceanography was a leading pioneer in this survey, and National Institute of Ocean Technology was a leading pioneer in developing the technology. So from 1986 onwards, several underwater technologies, because we are talking about 5,000 meters water depth, so they developed each by each several technologies with the international cooperation. But then, like I said before, the numbers that I showed in the previous slides, what is the cost? What is the cost of extracting these minerals? India did develop technologies. They did retrieve about 200 tons of nodules from Central Indian Ocean Basin. Did develop the technology for metal extraction, but then it did not make much of an economic sense for a much larger period of time. So they waited low and then laid low, and then now with this green energy focus and the strategic minerals concentration with different countries, again it is picking up, and that is the reason the deep sea ocean, deep ocean mission is now initiated by India to again look at and mature the technology and then be ready to extract these. So what are the innovations? What are the ideas? How do we go around and pick these nodules or the minerals from the deep sea bed? In this picture, what it shows in this picture is, this is a system. You have a mothership, which is placed in the area of mining, and you lower a crawler kind of a thing. It's like a deep sea crawler. This has, like you see here, you have a collector in front. The nodules are strewn on the seabed at whatever depth they are available. They are like potatoes half buried in the clay or sand. There is no sand at the depth, but half buried in the clay. So the purpose of this crawler is to go ahead and then pick these nodules together with the mud, take it up, and there is a crusher here, and then either a crusher or a washer. It washes or crushes and then pumps it up to the mother vessel through this umbilical hose. So this is a simple example of a deep sea mining. There are several technologies that has been tested, tried and tested, but this is the one that India has been looking to. So what is the evolution of the Indian mining machine? The National Institute of Ocean Technology started with testing a simple crawler off the coast of Goa and the Andrea Bank at 100 meters, 30 meters water depth. They tried the locomotion, they tried the pumping. Then the cycle kept on continuing because various challenges kept happening at each stage of it. And today, this is the final form of crawler collector that National Institute of Ocean Technology has developed and is under development and testing. This is an integrated mining scheme that National Institute of Ocean Technology is testing out. You have a mother vessel, they have a research vessel platform, which is very unique and purpose-built for these mining system testing. And you have a huge handling A-frame, which is about 60 tons of safe working load. And then you have a system, which is, here is a crawler, what you see here. And this is an intermediate pumping station that is in between. So this one picks up nodules from the seabed, pumps it up to the intermediate pumping station, then it sends it up to the mothership for collection. This is the integrated mining system of National Institute of Ocean Technology. There are some pictures here. This is the actual picture. This was tested in the March 2021. This March 2021 in the Central Indian Ocean Basin. This weighs about 12 tons. And you have the tracks which walk on the seabed, and you have the collector at the front. And these are the buoyancy packages which lessen the weight of 12 tons, because if you put the 12 tons on a slushy mount, the whole thing would sink. So to make it lighter at the underwater, they add syntactic foam to make it lighter. These are the several handling systems which handle this one. These are some photographs from the operations. What are the key challenges and what innovations that they did in this development of this mining machine? The key challenge is the soft soil. At 5,000 meters, the bearing capacity of the soil is so low that a 12-ton weight will sink about 2 feet it will sink for about 2 feet. That's what they found out. So whatever they design for the locomotion, the tracks, belts, everything sunk in the first attempts. Then they improved upon the design and made it lighter by means of syntactic foam, so it could sit on the floor and start the locomotion. Then the next challenge comes up. It's not like a classic mining where you cut the sand or you dig the sand and then set it up. The nodules are just half buried lying in the ocean. It's like a cherry picking from the ocean bed. And you need to either pump these potatoes up or crush it to a slurry and send it up. These are the key challenges, and they came up with several solutions like airlift system, hydraulic lift system, centrifugal pumping system, and then they have zeroed on a slurry pumping, partial crushing underneath, and then setting it up. And then how to sustain this motion, because it's not just one time. You go roll over and then pick up something. It's a commercial. We are talking about commercial mining. We need to have several tons of nodules to be picked up in an hour and then send it back to land for processing and then taking the metals. So all this thing has been designed for that. So coming to the mining vessel and the mining platforms, like I said before, along with India, European Union also has realized the deep sea potential that is available in the Pacific Ocean, and they have together with the IHC in Netherlands, they had this blue mining and blue nodules project, and they developed specially designed platforms with key challenges to address in these deep ocean, because the oil resources that we talk about are in the or proximity to the land, and they are very close to the land, and they are in the shallower depths, whereas these resources are in deeper depths. So this calls for a special platform designs, and IHC has executed these projects. And then similar to what India has done, they have developed technologies for collector, they have developed technologies for pumping it up, they have developed technologies for storing, onboard processing, and sending it out. But all of this thing comes with a pinch of environmental concern. I also want to take you through the another mining project that happened in the world. That is the Papua New Guinea mining project, where they dug for copper and gold. There was a huge project called Nautilus, which was taken up with the Papua New Guinea. Papua New Guinea as a country gave permissions for mining, and then the Nautilus Corporation, together with funding from international agencies, designed a mining vessel. And then this is a PNG mining vessel. They designed a mining vessel. They built a mining vessel in China. They built this seafloor production equipment, and then they were ready to go for mining. But then the Greenpeace initiative came, and then they had a huge concern on the environment. We'll see about that a little bit later. So just on the what is very interesting about these mining vessels. I talk about this PNG mining vessel only because it's been built. So we can have a look at these sizes of this. It's about 227 meters long and 40 meters breadth, has a ore carrying capacity of 39,000 tons with a crew capacity of 180. They have an onboard power of 30 megawatts. And so one of the huge handling equipment is 200 tons anchor handling AHC crane, active heave compensated crane, plus several of the seafloor production equipment, like what I showed, picking up and then crushing and sending it up. This was designed by CTEC Solutions in Singapore. It was built in Mumbai shipyard, and the vessel is ready. It was ready to go to sea to start the operations, but then the whole thing came to a stop because of the environmental concerns. So while we look at this platform, what are the platform challenges? Because we have been associated with this, and I've been associated with the National Institute of Ocean Technology to develop their platform Saga Nidhi. What are the challenges that we went through, and what innovations that what did we do to overcome all these things? One of the main key platform challenges is the multiple vessel dynamics. When we talk about the mining, we need to talk about picking up the ore, concentrate the ore, and then process and then transfer to a carrying vessel. Because like I said, some of the mining sites are a few thousand kilometers away from the land. We need to carry the ore back to land for mineral processing, metals processing, and then extraction of metal. So then we always need multiple vessels to be at the site, and we need to have a vessel-to-vessel transfer. And multiple vessel dynamics is one key challenge, and we need to have a dynamic positioning for all the vessels that operate in this, so that we don't have an event at that particular point of time. And then always, most of the time, weather window. How do we design the platform for the weather window? Because the mining is a continuous operation. Once we start, it's very difficult to discontinue and continue again later. Even the winding down the operation could take a couple of days, and restarting could take a couple of days. Then we are losing vital production time. So how do we design the platform to operate in all weather, almost immune to the weather? This is one of the big challenges, and this still needs to be addressed and overcome with this. Like I said, distance to the mining site, some of them are 5,000, 6,000 kilometers. So we have a huge problem there. because anything that you carry there, you resupply, repair, and service, everything will be a problem at that particular point of time. And then we have the depth to cater to. Most of these minerals are in the region of more than 200 meters, some are in 1,000, some are in 5,000. And you are having a mother vessel always tethered to the seabed. So the safety of the platform is another question. If there is a cyclone or hurricane coming, and what do we do? How do we protect the platform itself? This is one big challenge that we need to address this. But then it's always the collection. Even if you are successful with the mining technology, we need to process the ore. We need to process the ore and transfer to the land. And then comes the discharge of the processed refuse. Everything, because when it comes to ore processing, we are always talking about discharge. How do we safely discharge this? And how do we keep the continuous process going? Because we are talking about long distances, we need crew transfers, we need human comfort, we need continuous process to work. These are some of the challenges. Some of them have been addressed, and some of them have been addressed only for experimental basis. When it comes to commercial mining, several of these questions still pop up, and there is a huge opportunity to discuss each of these ones. And when it comes to one of the big challenges is the energy resource. Even for operating this mining platform, we need to have energy resource, and these energy resources need to be replenished. So like this lateral ship design, naval architects have this concept design platform here. Several of new ideas need to be looked at, like liquefied nitrogen, fuel cells, batteries, perhaps solar panels. So we need to find energy resource which will minimize the turnaround time. So what I always say is we need to have very different innovative ideas. That is the need of the hour for the future platform designs. We need to have renewable energy source, extending the turnaround time, like I said in the previous slide. Any of these different fuels from the fossil fuel we need to have so that we can extend the time at that particular point of time. Then ore concentration, metal extraction at site. What are the possible? We always look at the classic ore extraction and metal extraction. But can we do it at site? Can we have a production or a factory vessel at site and then only transport the metal? What will be the economics? What will be the platform considerations for these kind of factory vessels? And how do we work these factory vessels at such a large distances from the land mass? And then again, then next comes the question of safe disposal of the waste or the process wastage. The process wastage, there are several ideas for the process wastage to be disposed of. The easier and the cheaper ones is to let it out in the ocean, but then there is a huge environmental impact that comes from that. And several institutions and the entire world is concerned about environmental impact. So that one question needs to be really hardly addressed. Maybe can we have an innovative ideas of making the waste into a capsule, concentrating the waste, and then burying it deep in the ocean where we extract. And whether that will have a lesser environmental impact footprint than the disposing in the sea. Can we carry it back to the land? What is going to be the cost considerations? This one safe disposal of the process waste could be the deal maker or deal breaker, even though we have a technology like the PNG Nautilus project. Then again, we have been talking about technology that has been working with the classic power from the mothership to the crawler, high voltage power. Then can we have leaderless autonomous shuttle mining? Can we have like autonomous underwater vehicles just going around, picking up the nodules, doing some semi-processing down, and then coming back to the mothership, depositing the ore? This will address several of the concerns that I talked about in the previous one. Then again, you need enormous amount of power for these autonomous shuttle to work for a decent period of time. And here comes again the question and the innovation. Can we have innovative power for this autonomous shuttle mining? rather than the classic battery solutions? Can we have fuel cells? Can we have hydrogen-powered shuttles? These are questions where there are no answers today, or not even projects that are running in those directions. These are the opportunities for projects to run in these directions. And then again, coming to the platform itself, we always talk about the monohull vessels or monohull vessels for these applications. Can we have deep sea TLPs, moored platforms, similar to the offshore platforms, say at the 5,000 meters? Are they feasible? These are the questions. I mean, this could open up several avenues for design, because today it doesn't exist. It exists on medium depths. So it just opens up these kind of questions, opens up ideas for working further. Like I said before, environmental concern is the biggest challenge in this entire one. And like environmental disturb to the process of ore picking up in the deep, that's what happens. And then even when we concentrate ore in the mother vessel, we have problems with that. What India is doing is, India is developing under this deep ocean mission a manned submersible that is capable of working in 6,000 meters water depth. There are only very few countries in the world who have this technology, who have this manned submersibles. India will be joining the Select Club when they develop and test. The National Institute of Ocean Technology is doing it. That's the picture that you see here. This is primarily being developed to study the environmental impact, because India being a very concerned nation, they want to study the complete impact before they exercise that right from the International Seabed Authority for deep seabed mining. So here it is, the opportunities to work in this deep sea mining and extraction of minerals. So that's it. If there are any questions, I will be very happy to answer.
Thank you, sir. This was what do we say? A fascinating 25 minutes. We keep listening to various sessions, and you think you know something about everything, and then you come across a new subject where I suddenly realize that the facets of this I have personally never even comprehended, and I'm sure that a lot of our viewers today will agree with that. Just the sheer, I would say, the challenge and in a way audacity that we as human beings are even imagining and taking to this level. I mean, we are going into moon exploration at Mars, but in our own oceans, there is so much that we know nothing about. So I can see this as a fairly big step. Of course, it's also very interesting to see that India is doing a lot in this area, and we could be leaders in this. A quick question to start with: is there any country in the world that is already mining and obtaining these nodules from the sea?
The answer is no. There are no countries in the world which are actively mining and obtaining nodules from the sea. There are several countries who have developed technologies. The idea is every country wants to develop the technologies and keep it in the shell. Because like I said before, it did not make much of an economic sense to extract metals or minerals from that deep, even from Pacific, which is 3,000 meters. But then today, again, they are coming back. This happened in the late 90s, but today into 2020s, again, it's happening with several countries in European Union as well as in India because of the huge demand for this EV revolution. So they again think that it could make an economic sense or a strategic sense to go back to the sea. So again, they are investing money and doing it, but no commercial mining is happening today for the nodules for which any of the countries.
Understood. Okay. A couple of questions from our delegates.
Yeah.
I'll just read out the first one. What do you think is a considerable invention in utilizing wave energy? Will it satisfy the energy requirement? You were mentioning about supplying localized energy for the platform. So the question is, will wave energy be adequate, or can it be used?
Excellent question, I would say. utilizing wave energy because waves are perpetual, they are always present in the ocean. But then India has carried out wave energy experiments way back in 1990s, and we still have an experimental plant running in the coast of Kerala, Villingam, which produces wave energy, and several countries are going for innovative wave energy. But what I would say is the energy density from the wave energy is way too low to consider powering. Perhaps that's a way for even for solar. And what we are talking about, like I showed you, that we are talking about energy densities of 30 megawatts for a small mining vessel, experimental mining vessel. So I feel the energy density will be low. But I never ruled out this because wave farms, like wind farms, are being tested out. And like I said, this is again an opportunity. We need a proper study to see if it is possible to do that. And especially in the areas where the nodules are available, we have more of swells rather of waves. So the energy density is even more lesser.
Okay.
Yeah.
We had a session yesterday where the option of nuclear power was being actively discussed and looked at, given a lot of emission requirements coming up and the need to go into zero emissions. So perhaps that may also come up in this environment. Next question is from Mr. Venkatesh Naidu. Is Fiats India into manufacturing of these deep sea mining equipment?
No, we are not in the business of manufacturing in this. Fiats is engineering and consultancy firm. We are into manufacturing products, handling systems, but not necessarily these mining equipment. No, we don't manufacture.
Okay. The next question also is from him, and he's asking, how are the compressors run underwater?
Compressors? I thought there are no compressors in this mining machine. The mining machine underwater just picks up the nodules. Nodules, like I said, are like potatoes. They are washed, and the sand or the clay and they are separated. And then if there is a choice for the company whether to crush it underneath or send it across as a whole potato to the mother vessel. So there are no compressors. Usually, either centrifugal pump or inline pumps or positive displacement pumps are used to push the slurry up to the seabed, up to the mother vessel.
Right. Okay.
Yeah.
Another question that comes up to me is, given the depths where you have more than 5,000 meters, you did mention about the consideration of anchoring this, but given these depths, would it be more likely that the mother vessels would be like a dynamically positioning vessel where they will have to be continuously on standby, like we have the diving support vessels?
Yes, question well asked. That is the idea today, not to move the vessel to the seabed, but to keep it on a dynamic positioning, keep it hovering like the diving DSPs. But then, as everyone knows, keeping on the DP all the time on standby is a huge consumption of fuel. And we are limiting our endurances at that particular point of time. That is the reason I suggested that it needs different out-of-the-box thinking. The one way that you move the vessel through a tension-like platform, TLPs, means that you're eliminating the need for being constantly powered up. Then your energy demand keeps going down. Your energy demand is only for living, as well as for ore processing, as well as for ore picking, but not for keeping your position. So that is the idea. But then today, mooring is, I don't think technology is so matured or not even anybody has tried mooring a vessel at 5,000 meters depth. No.
Correct. Mr. Arvind Ganeshan is asking whether there is any private sector involvement in this whole process, or is it purely a government initiative?
In India, it is purely a government initiative. Though they take along private enterprises as suppliers, there is no collaboration of private industry in the Indian mining program. But abroad, in the European Union, as well as in the other countries, private entities are partners to the program for the government. Like for example, in Netherlands, IHC is an active partner. They develop the mining ship as well as the mining machine. So it's a different model adopted in India.
Okay. And what is the size of these modules as they're pumped up? That's another question from Kamal Palit.
They are about, they start from even 2 centimeters to about the maximum size is about like 10 centimeters, 6 to 7 centimeters.
Okay.
As a typically, you can see a bag of potatoes. That's the size. Yes.
And you use centrifugal pumps to create a slurry and push them up.
Yes, they also use 2 technologies. One is hydraulic, another one is airlift. What they do is they also inject a little bit of an air when you pump water together with these nodules. The air creates a little bit of a buoyancy and carries these potatoes up the riser. That is the airlift system. And the pure centrifugal system pumps the water together with these nodules up. They are slightly, they weigh lesser than the normal rock. So the density is very less. So they're able to come up to the surface.
Okay.
Yeah.
All right. There are a number of questions that come up, and I'm sure that our viewers also would be having a lot more to ask now that we've got a glimpse of what this entire technology and process is. Thank you so much for enlightening us, Mr. Jankiraman. And
thank you.
Look forward to having more discussions with you. And we hope that this progresses for India also. Thank you so much.